Thank you so much for the nice introduction. Also, thank you for inviting me. It's a really nice, exciting opportunity. As said, I want to talk a little bit about the species scale, but not like what the species scale is, because I think most of you or all of you are pretty much very much into that topic. So I don't think I need to introduce it so much. However, I want to link the concept of the species scale with a little bit more of like other concepts, just as the towers of infinite light distance towers and black holes, for example. For that purpose, is this not working? For that purpose, I want to basically put my talk into two parts. The first one is about the moduli dependence of the species scale, where we can define the moduli dependent species scale in two different ways, namely in the way of the genus 1 free energy and the corrections to the black hole entropy. From these two Ansätze, basically, we can define two different ways the moduli dependence of the species scale, and we will see that it actually fits together quite well. And the second part of my talk will be about a more recent concept, which is the CRB pattern, discovered by Castellano, Nacho, and Venezuela. And we have computed some corrections to that pattern, some subleading corrections. And because the species scale is a very well-motivated concept in moduli space, we were asking ourselves if there's like other patterns or other directions where we can actually probe a similar pattern, also maybe in the interior of the moduli space. We try to do so. If it worked or not, you will see at the end of my talk. And then in the end, of course, I will give a discussion, I will give a conclusion, and a little bit of a further outlook in what will happen next.
Yeah.
In hopefully species scale.
But again, these are the 4D ones.
Sorry? Oh. Hopefully like species scale research, and also like what I plan to do in the future. So just because I can't not introduce the species scale, but I'm sure you're all very well accustomed to it. The species scale is the cutoff scale beyond which no EFT is reliable anymore. So even if you have an EFT which has a certain cutoff, and then you can find a higher dimensional EFT with a higher cutoff, at the end, you're gonna find the species scale, which tells you like above the species scale, there's no EFT anymore. We can describe anything with. And the species scale is parametrically smaller than Max Planck if there's like towers of many like degrees of freedom. So like the emergent string conjecture tells us either you have a Kaluza-Klein decompactification, or you have winding strings, which pushes the species scale below the Planck, the M Planck. And you can see in the corner the relation for the species scale. This is in like whatever dimensions you want to be in. We will focus on 4 dimensions, so don't be scared if a square root pops up. This is just because we're in 4 dimensions. Also, there are many people listed on this slide. I'm sure I've missed so many more people. I'm very sorry about this. Please text me after and complain. But at the core of the species scale research, or at least on my interest of the species scale, is how does it depend on the moduli that we have in our string compactifications, and also, again, linking to patterns or linking to universal behaviors, can we exploit them to study our swampland conjectures more and study our moduli space more? Because moduli space, like the infinite distance limits, are pretty well studied. I mean, there's way more things to do than we already have, but the interior of the moduli space is unfortunately not so well studied. So maybe if we have like some quantities that are also motivated within the moduli space, we might be able to get some more information on how it looks within the moduli space, which would be amazing. The first part of my talk, as I said, is about the moduli dependence of the species scale, and I have to mention the paper by Damian, Kumrun, Max, and also Wu. There's a couple of papers, and the goal of them was to exploit the properties of type 2 string theories compactified on a Calabi-Yau threefold. And the species scale, they have shown that it can be related to the genus 1 free energy, F1 of the topological string, in such a way that you can see on the slides. And again, the square root is because we are in 4 dimensions. And the number of the light species will directly in 4 dimensions go with the genus 1 free energy of the topological string. This was one result that they have. And again, we try to look at kind of the same thing from a different angle, namely from the corrections of the entropy of a black hole. And what you get from that is actually quite cool because you get the same formula. But we have to be a little bit careful because not everything that looks alike is alike. It's still an F1. Unfortunately, it's not the same F1. It's the F1 that you get from the generalized pre-potential, which is also dubbed F. And it's the first order correction, giving you basically the same formula, but we have to be careful with identifying these Fs. At the end of the section, I will tell you whether they coincide or not. I think you probably know by now, but this is a little cliffhanger until now. How did we compute these kind of moduli dependencies? We start, as I said, from a generalized prepotential. We chose a prepotential like this, which is type 2a on Calabi-Yau. We have our vector multiplets, we have our triple intersection numbers, and then the last term that you see there, so the first term is the normal prepotential without corrections, and this is the correction term, and the di is proportional to the second Chern class. Again, we want to study if the corrections do anything with the entropy, if we get like lower bounds or anything like that. Turns out if you actually compute the entropy via the Wald formalism, you get something like this. Again, the first term is basically the uncorrected side. The second term is the correction that comes in. We have to be a little bit careful here with the notation now. These are all sums. So the i's are summed, and here also the i's are summed. Everything is like Einstein's sum convention. This will come clear later where I stress that. But as you can see, we have a corrected term and we have an uncorrected term. What we did now in order to see if we can have like kind of bounds on the entropy or kind of like play around with it a little bit, we set all p's to 0 except for 1. So what would happen if you wouldn't have the term, if you wouldn't have the corrected term, is the entropy would just get 0. So you don't have a lower bound on the entropy is just 0. However, if you actually factor in the correction that we did via the Wald formalism, we get something like this. So here, careful, these I are not summed anymore. It's just one pi that is not 0, and the other p's are all 0. This is why the first term cancels out. If you choose to do something like this entropy is non-vanishing. So like for any p that you choose that is non-zero, we actually find a lower bound on the entropy. You could also argue, well, yeah, if you do that, you kind of have small black holes, so you have to be a little bit careful because you picked one correction. What if there are other corrections that are just as valid? And this is a valid question. However, people, also Carmina here in the audience, who will speak after me, have shown that even if you include all corrections, it doesn't not matter, but you get the same thing, so it's fine. What we do with this kind of lower bound in the entropy, it is possible to connect this to, well, again, it comes from the corrections, and the corrections with this lower bound is possible to connect to the number of species that we have. So we have, again, the same formula, the lambda species over Max Planck equals 1 over square root of F1, as I said before. But what kind of F1 is this? This is the F1 of the corrections. What does that mean? We still don't know whether we can correlate the F1 of the corrections and the F1 of the topological strings, but there was a conjecture that is very helpful for our purposes by Oguri, Strominger, and Waffer in 2004, which states that we can basically relate the black hole partition function to the partition function of the topological string. And if you think that is true, or if you believe them, we can directly equate the F1s together, and we have one formula from both sides. So what is cool about that is we have a moduli dependent expression for the species scale from 2 different angles, and they correlate perfectly. So this is something very nice about the species scale. This was the first part of my talk. I think it would be better if there's any questions on this, like if you speak up now, because I will switch gears now. I don't see any questions, so I will switch gears and go directly into the pattern that also Nacho worked at. This is an empirical pattern in the moduli space, which links the logarithmic gradients of the mass gaps of the light towers to the logarithmic gradients of the species scale in infinite distance limits. So basically, we have this kind of pattern that you can see on the slide, and in many sorry. Yeah. Okay. In many examples, we can see that this pattern holds true. If you take the logarithmic gradients of the mass gaps of the lightest tower and the logarithmic gradients of the species scale, you get 1 over d minus 2. Again, in the future, we will mostly set d to 4, so we have a 1 over 2. This is almost cool because we have our species scale that is also motivated in the, or like well-defined in the interior of moduli space. However, the light towers that we put into the MT, or the lightest tower that we have there, well, they're only really valid asymptotically in infinite distance limits because there's like one tower that goes light that we can put in there. So it would be cool to find something that is universal or also like in the interior of modular space. However, I don't know if we can do that with such a relation, but we will see. So what we did with that, we computed the subleading corrections to that pattern. Our first setup, well, basically we did 2 setups, but I'm going to present you one of them, the easiest one, which is the isotropic torus. So we have 3 tori, we have our Kähler potential, we have our free energy, and we have the mass of the lightest tower. Here you can see some weird symbols, also called Greek letters. The gamma is for our cases is 3 because there are 3 torus, and we look at an isotropic torus, and the moduli t is basically x plus iy. We will take the imaginary part y to be large. But basically we have 3 times the same thing. So this is why gamma is going to be 3. However, we chose to keep it general for later purposes. And also for this kind of calculations, the gamma drops out. So it really doesn't matter so much for the torus. Also, you can see the beta. The beta is a little bit more conceptual because it basically encodes information whether you want to look at the massless modes of the free energy as well, or whether you leave them out. It has been argued that in the free energy, you should not put in the massless modes, because if you do, it leads to infrared divergences, which we don't like. So if beta is 0, this basically corresponds to neglecting massless modes. They're gone out the window. And if beta is 1, we account for them. And we will see that this kind of difference actually makes a difference. Like, who would have thought? We will account for them and put different results from these kind of distinctions. Wow, that was too fast. Sorry about that. Exactly, and this is the paper where they motivate that the massless modes should be not brought up in the free energy. This is our, well, basically result. You can see the term highlighted in red is the term proportional to beta, which will drop out if you say beta is 0. So if beta is 0, well, let's start with beta is 1. So we actually account for the massless modes, and you can see that the subleading term of this is the one with the log. This is parametrically larger than anything else here, and it is also positive, always. So if you have the massless modes in your calculation or in the equation, you get the pattern. Well, first of all, you get 1/2 asymptotically, which is already amazing. But if you have the massless modes in, you always approach this 1/2 from above. If you, however, integrate them out, or like, well, not integrate them out, but if you leave them out, you get something not quite so straightforward, because then the subleading term is the one after the 12th, and this is a cosine. So sometimes, depending on the values of x, you approach it from above or from below. So it's not so clear cut, like if you always are below the 1/2 or always are above the 1/2, if you leave out the mass modes. As I indicated before, it would be really, really, really cool to see whether we can have another scale that is kind of like our light towers. So like kind of like MT at the boundary, but more better motivated in the inside of the moduli space, because if we have that, we have two quantities that are motivated inside of the modular space. And actually, we have found such a scale, or basically other people have found it for us. This is the black hole scale by Bedroya, Waffe, and Wu. And they have motivated the scale on the grounds of the Gregory-LaFlamme instability for black holes, which basically tells you if the mass of your black hole is low enough, another class of solutions with lower free energy appears. And this class, again, is missed by your lower dimensional EFT, leading again to a cutoff, because then it tells you your EFT is incomplete. So you have another cutoff set by this black hole scale, which is per definition lower than the species scale, which is lower than the M Planck. So this is the kind of hierarchy that you have. This black hole scale is the transition scale between the higher and lower dimensional black holes, and its property is also that it agrees with the lightest tower in weak coupling limits and also in large volume compactification limits, making it our playground that we wanted in the first place. Because from these kind of, well, assumptions, or these kind of like starting points, we can assume that a similar pattern might hold in the interior of the moduli space, the similar pattern as to the pattern by CRV, which you can see on the slide now. However, there is the problem that species scale actually has desert points. And with these desert points, the derivative would go to 0, and the black hole scale, or the derivative of a black hole scale, would have to blow up to account for this, if this would be a sim. So if this was the relation that we have, something weird would happen with a black hole scale. That's why Bedroya, Waffe, and Wu argued that this should actually be a smaller than, or an equal than. So we have a little bit more leeway in how the species scale behaves, because it's said to have desert points. Long story short, we have another scale that we can throw in our pattern story, and we can look whether the corrections hold up, how they hold up, why they hold up, and what that implies for us. So the first step that we have to do is actually get the black hole scale that we want to look at. And we can do that by equating entropies of a higher and lower dimensional black hole. This is in the microcanonical description. So in the canonical description, it would be the free energies, but in the microcanonical, it's the entropies. Yeah, would be the free energies. In the microcanonical, it's the entropies. And we also have to include the Gauss-Bonnet corrections, because these corrections encode the information that we want to look at, the corrections. This is a lot of formula, I understand. This is a long calculation, and the end of it is actually quite simple. We find our black hole scale is equal to the radius of black hole inverse. And again, as we predicted, it kind of scales like the light towers, but it has a correction proportional to the Gauss-Bonnet terms to it. There is a caveat with this thing. We do, as I said, we have this gamma, which tells you like how many tori you decompactify. And it sets that gamma bigger than 1 might be inconsistent with the asymptotic values dictated by the immersion string conjecture, because it might restore too much SUSY for the relation with the for the species scale relation with the genus 1 free energy to hold up. That's why we focused on gamma equals 1. However, this correction, unfortunately, is not small for gamma equals 1 because alpha is proportional to y, to the modulus that we take large. Remember, the modulus is t, which is x plus iy, and we take the imaginary part y large. And the mt, there was a slide very much before here. You can see that the mt is actually proportional to y times minus 1/2. So if you have mt here, mt squared, this actually gets rid of the moduli dependence, and it's not gonna be so small for gamma equals 1, even in infinite limits. This is gonna come back to haunt us. Nevertheless, we computed the corrections to the black hole scale. We are very happy that asymptotically it still holds up. We still get the 1/d minus 2 or 1/2 in 4 dimensions. The epsilons are the terms that we calculated before in the isotropic torus. So everything kind of looks the same. We get just additional corrections that you can see in the end. You might notice that there's only one negative correction. And this correction is proportional to 1/y squared. So it's gonna be always subleading to the corrections that we had before in the epsilon terms. Because these corrections, depending on whether you put the beta to 1 or to 0, it's either log or it's gonna be like e to the minus without the y squared. Thus, we cannot say in either case, because remember, even for the b equals 0, I mean, for the b equals 1, it's always going to be approaching the pattern from above. So this kind of relation, which we can see in the right upper corner, it's going to be violated anyway. Like if b equals 1, this is violated. And also if beta, if beta equals 0, it has regimes where it's also violated. It's sometimes satisfied because sometimes it approaches it from below because of the x values. And sometimes it is not satisfied. It approaches from above because it's, I can maybe quickly show you again because it's better. Again, there's this cosine and it approaches sometimes from below and from above. And the black hole corrections cannot change anything about this because it's subleading. So is this conjecture with the smaller than to be refined, or better said, wrong? The short answer is, and the honest answer is, we don't know. We can't say because of what I told you before about the gamma equals 1. It's a kind of conspiracy that in the limit where the F1 can be related safely to the lambda species is actually the limit where we cannot trust this correction. That is a little bit sad, but that is what we got from there. So the conjecture is not yet proven to be wrong. We cannot trust our limits. Concluding, I think I'm very well in time. The species scale is still a rich playground for investigating all the swampland conjectures and the moduli space, and there's much more to be done, also with the pattern, also with other scales and like relating other scales. So the main question still is, can this pattern be continued within the moduli space? And what about the desert points that came to haunt us as before? This is the general thing that would be very interesting in regards to species scale and regards to moduli spaces for me. And also more, well, egoistically, what I still work on is connecting entropy and species number again, still for fermionic black holes and black holes with a tower with multiple charge species, which is an ongoing work with Ivano, Dieter, and Joaquin. And also there's the phenomenology side, which, for example, investigating the dark dimensions, which also introduces cutoffs on your EFTs, which is also ongoing work with Nicolo and Dieter. And with that, I think I kind of threw everything I had at you. Thank you so much for listening, and thank you so much for inviting me again, and I will be up for questions now.
Bye. Thank you, Georgina, for the very nice talk. So let's see, now we have some minutes for questions from part of the audience. So people just like raise your hand or unmute yourselves. But in the meantime, while they do, I'm gonna take advantage of my position as chair today and ask you directly a question. So you mentioned indeed the argument from the Harvard group that says that at some point in the desert point, the species gets to a maximum and that the pattern should be zero, the product. But could you expect something similar to happen for black holes? Like, would you expect for it to for some maximum to appear, or even for that black hole scale to be a continuous function, maybe in some limits of moduli space is some type of black hole, in others is another? Is this transition between the two smooth?
You mean if the gradient of the black hole scale actually also has desert points?
Yeah, or if it's even like a smooth thing that can be defined everywhere.
Naively, I would not think so, because you have it's sorry, because it's coming from the entropies, right? Okay, sorry. Because it's coming from the relations of the entropies, which I don't know. I don't think there's going to be a desert point like this, but I'm not sure about this. This is a good question.
Yeah, I mean, I was thinking that maybe like imagine if you have, I don't know, with the type 2A or
Yeah.
well, description that you have. Well, here you have two. One is an emergent string limit, but imagine that you have like one limit is some perturbative description, and in the other direction is a different one. And I wouldn't say that necessarily like the lightest black hole should be the same. So I like the transition between the two regimes, whether there's something that you could say once including these corrections, whether there was something to be said about that, but it's fine.
Yeah, I think it's a very interesting questions, but I have not thought about that, to be honest.
Okay, fine. Okay, so I think now we have